start with the RAL model. Do you have any doubts in the before session? Anyone? Everyone clear with the config DB and factory registration concept? Clear or any doubts? Yeah, am I audible?
Till now, yes, ma'am. Till now, it's okay, ma'am. If any doubt arise, I will ask.
Okay. Did you got the clarity, everyone? Have you referred the recorded sessions? Hello. What about Vishal, Yash, Shamim, CB, Gurshant, Sheetal, Tamanna? Tamanna, have you gone through before sessions?
Hi, Prashanti. Good evening.
Yeah, good evening. I think you didn't join for I think you didn't join from last 3-4 sessions. All our major topics in UVM. From phases I think you attended. After that, factory concept or TLM ports.
Yeah, I could not join. I mean, I tried, but I couldn't join. But and I have not been able to go through the recordings yet as of now. But I started, uh, trying those examples that are given in the PDF. So I'm just trying to catch up.
Mhm. Okay. What
If
about
I
Vinity?
if I have any doubts, I'll share in the next session, most likely.
Yeah, sure. Okay. Okay, sure. Okay, fine now. So today we are going to start with a RAL model. Actually, today we need to discuss on reporting mechanism. But before reporting mechanism is very simple. Just a few topics only. But before that, we will discuss on RAL model. RAL model we need to discuss in 2 days. Okay, so as per our schedule, RAL model is for 2 days. So first today we will discuss overall theory part for RAL model, and in the next session we will discuss on coding part. Okay. So can you tell me what is mean by RAL? So what is the basic idea you have?
Register abstraction layer.
Okay. So what is mean by register abstraction layer and why do we use that?
Uh, from my understanding, whatever from the little understanding I have, uh, I think that in UVM and in PSS also, I work for PSS. The memory is stored in the registers. There are abstract registers in this methodology, and we perform all those kinds of operations, read and write, and um, you know more operations that are performed on registers. So that is what I know.
Okay. Any other answers from others?
I
CB?
mean, DUT, we have registers, we have some RAM and all. So to verify that, we are using RAL model.
Okay, fine. That's it. Huh? Okay. So if you see like a normal programming style, so before we have worked on adder or some counter logic, different type of normal combinational logic circuits or flip-flops, counters we have designed in UVM, right? So how we design, just sequence, there will be a sequence and sequencer. Through the sequence we have generated multiple number of test cases or sequence items, and we send to the driver through sequencer. Okay, that is what normal data in the sense of binary values. Okay, so in system verilog we randomize through a generator. So what is a generator?
It generates the transactions.
So in generator, we do the randomization. So whatever the randomized data is there, that data we will send to the driver. Okay, suppose we are randomizing data, address, enable signal, and write read signals, some pointers, everything. Suppose address is there. So what is the address we will generate? Like a 100110, something binary value. Like the data also 1000, like that, some binary value we will generate through the randomization and we will send to the driver. Okay, not only address data, suppose a value, b value, c value, suppose adder we have designed, a b will be the inputs. So normal binary data we will do the randomization and send to the DUT. Okay, but in most of the projects in SOC level or IP level, or even like a memories like RAM, ROM, FIFO memory. So coming to the memories specifically, every design, every DUT or every architecture, there will be some combinational logic circuits like ALU, multiplexers, and sequential logic circuits like counters will be there, synchronizers will be there, like that registers will be there, general purpose registers will be there, special purpose register will be there. So everywhere we find the registers, even in the processor also. Whatever the processor we are designing, suppose any processor, there will be number of cores, internal cores, there will be instructions. Through the instructions only, every communication will be happen from processor to the normal functional block, right? Suppose if this processor want to communicate with the memory, so how it can communicate, the handshake between the processor and memory will be happen through the write and read operations. That write and read operations, how it will be happen, here we need to write the instruction. So instruction set architecture, you can write any instruction like immediate type or branch type, jump type, register type, whatever. Suppose I am writing a instruction call, add addition of R1 is a destination register, comma R2, R3. So addition of R3, R2 will be stored to this adder. Like that, this is a immediate. Immediate means you will be having direct value here. Suppose if you are taking register instruction set model, then it will be having the registers like the branch type or jump type, whatever. The main thing is instruction. Through the instruction, we will store the data, we'll do some operation, ALU, arithmetic or logical operation, and we'll store the data into this register. Okay, so this register, whatever there in the processor, same register will be there in the memory also. Okay, so from this register, we are sending the data, we are storing the data into the memory. That's what handshake. Just data transmission will be happen through the protocol or whatever. Okay, so instruction sending to the processor or memory or any other IO peripheral, whatever, just like how our human brain is sending all the instructions to the body, to all the signals, even small nerves or whatever, even from top to bottom, whatever the part like hands or legs, wherever, just sending the information and getting the information, transmission and receiving. Okay, so both the transmission and receiving will be same information, whatever the brain is giving to, suppose I am talking something, whatever I am talking out, that would be given from my brain. Whatever I am talking now, this output signal also will be listening by the brain, so same signal will be getting transmitted and also receiving. Okay, here also whatever we are doing, some transmission from processor to memory and memory to processor, that thing will be everything will be done through the registers only, because register is the main storage element. Even in the processor, whatever we are writing some instruction, if you see, if you may know microprocessor language, you have studied in your btech level, microprocessor language, assembly language programming we call. So all assembly language instructions would be written in a register format only. Okay, so everywhere registers would be most important. Wherever we write some program, we use the registers only, general purpose or special purpose, whatever. Okay, but in just a system log verification or verilog test benches, so we never use this RAL model anything. Okay, so whenever the complexity is increasing in SOC level, particularly to verify the registers, we are using this RAL model. Okay, in system verilog we don't have that also a limitation. Okay, to verify the registers also we have generated some binary data. Okay, even to verify the registers, even from FIFO memories or RAM, ROM, whatever, we just randomize the data in a binary. Okay, but for more efficient way to suppose if you see the register how it look like. So this is the RAL model. So reg model, in the reg model, if you observe how the fields will be there in each first of all, how we declare a register in terms of field, right? Suppose there is a memory of 4 bit, 4 down to 2 bidirectional, 4 down to 2 multi-dimensional. That means totally it have 8 different registers, 4 depth to width. Total there will be 8 registers. Okay, so we can call it as a 8 by 4 number of locations will be there, like that. Here if you see R1, R2, R3, just like a register fields, how many register fields will be there, and also register block and the memory related data will be there here. FA, FB, FC fields, just a like that. 4 down to 2, 4 down to 2 means 4 3 2 1 0, like that number of fields will be there. Then R2, how many number of fields, R3, how many number of fields. So address mapper, so for R1, R2, R3, what is the address map? So like that everything will be there in terms of address and in terms of data. So normally how we will pass the data, suppose it's a first location. If you see first location means 1x, what is the address value? So 1001 something, like that. Second location 2x, what is the address value? 1101, like that. 3x 0010, like that. Specifically in terms of address mapping, we will generate a memory map file in this way. Okay, but in the normal case, however we are randomizing some data using generator, we cannot able to generate like this, particularly location, address file and memory mapping. These things with the fields, we never do the randomization. Just a binary value, 4-bit size binary value or 8-bit size binary value, 16-bit, 32-bit, just that's it. Okay, particularly however we write a RAL model data, particular data we never generate by using the normal sequences. Okay, so for that purpose we are using a RAL model here. For high level object oriented programming, for memory map registers and memories in a design under test, we use this register abstraction layer RAL model. Okay, so what will be there in this RAL model? First thing is a sequence library. Sequence library in the sense, whatever the number of sequences are there, everything related to the sequences, it will be having a library. That means where we store all multiple data in one box. Okay, so that's what we call as a library. And second thing is a register model. There will be a register model in the RAL model. Next thing is a adapter. So this is what the adapter layer, we call it as a adapter layer. We will discuss one by one clearly. And there will be a predictor. Okay, so in RAL model, majorly there will be three blocks. One is a register model, one is a adapter, one is a predictor. If you see here, this one, predictor, top one. These are the three major blocks in the RAL model. Okay, everyone clear till here?
Yes.
Any doubts till here?
No, ma'am.
Others?
Ma'am, this diagram is different from the previous one. And previous one predictor and is not shown.
This is just a top level block diagram. This is the internal. I will explain clearly. As of now, whatever I discuss, is it clear?
Yes.
Okay. Now, first we will see about the RAL model. So what is mean by register model? I will draw you and show how it look like. First of all, RAL model consists of register fields. Register field in the sense before I have told you, right, how we draw that one. Register field, and it contains registers, and also it contains memory, and also it contains register block, and also it contains register map. Okay, so what is the difference between each? First of all, register field. Register field in the sense, suppose any memory we have considered. Memory of 4 down to 2. So this is what register field. So in this, suppose this memory size is a 8-bit size. In this 8-bit size, there will be 8 number of fields. Field 1, field 2, field 3, field 4, 5, 6, 7, 8. So in this 1, 2, this 2, 3. So 4, 3, 2. Only these elements we are taking here as a memory. 4, 3, 2. Try to draw from your side also. Okay, so these are the fields we have selected in a register. So this register size will be the 8-bit register size. 1, 2, 3, 4, 5, 6, 7, 8. Zeroth location, first location, second location, third, 4, 5, 6, 7, 8 till 7. Okay, so in these 8 number of locations, how it will be like, suppose you are considering as a 8 into 4. Okay, 8 into 4 in the sense it consists of a memory with 4 depth and each 8 locations. Like this, a memory will be represent. Okay, so register block means what? Whatever the memory block is there plus these fields plus registers. Registers in the sense, I told you before in instruction set there will be R1 register, R2 register, and R3 register. So these are some general purpose registers. Okay, so in this register block, it will be having register fields, comma, this memory, comma, all these registers R1, R2, R3. Okay, combinedly. And coming to the register map, in the register map what will be there? It consists of all logical offset address of all the register and memory along with the pointer of sequencer and adapter. That is what register map. Register map means it will be having offset address. What is the offset address? Suppose this is one field. Like that we have two number of fields. Field 1, field 2. Register 1, register 2. Two number of fields. So this one will be having one offset address. Suppose 0 into 0 0. Second one having some offset address based on how much incrementing you are considering. Suppose if you see risk processor, we always consider program counter as a plus 4, pc equal to pc plus 4. Okay, byte addressing, we always consider 4-bit incrementing. Yeah, like that if you consider same 0 into 0 4 for each field. Like that there will be lot of fields and there will be lot of memory blocks. Register 1, register 2, like that register maps, everything will be there, memory blocks. So every block there will be some like this up offset address. Okay, and with this variables, suppose which type of register it is, name of the register A, and name of the register B, name of the register C. So all this information will be there in the register map. Okay, so whatever the information is there in register map, same data will be there in the DUT also, in the DUT, because in the DUT whatever the registers are there, same registers we are verifying here. That means we are randomizing the same data and sending to the values, input values to the DUT. Suppose R1, R2, R3, three number of registers are there. So to verify R1, to verify R2, to verify R3. Suppose R1 is related to this particular offset address, R2 is related to this address, R3 is related to this address. So we are randomizing this particular address and sending the data to the DUT here. Okay. Everyone understood what will be there in the register map, register model?
Uh, so Prashanti,
Yeah. Tell.
sorry. So my question is, this memory block map, all this is being defined for a, let's say, a RAM, whose size is 4 down to 2. Can we say like that?
For each RAM, there will be particular number of registers. Suppose here R1, R2, R3, three number of registers I have taken. Um,
Uh-huh.
so R1, R2, R3, three number of registers I have taken. And there are suppose you are asking for RAM, right? Suppose in DUT there is a RAM 1 and
Mm-hmm.
RAM 2 and RAM 3. Three number of RAM memories are there. So in the DUT we will have these particular registers also. Register 1, register 2, register 3. So the one RAM will be connected to one particular register, another RAM will be connected to another particular register, and the RAM like this, R1, R2, R3, R1, R2, R3. So three registers will be there. In the same way, suppose in the test bench, you are creating some test bench. In the test bench, you need to create this R1, R2, R3. Three different fields you need to create. Okay, so register 1, register 2, register 3. So in the test bench, there will be reg1 related fields and reg2 related fields, and also these fields are having separate memory mapping, memory mapping in the sense where we have all the related offset data and the field data, and also it will be having the main top level memory. Okay, this is how we connect different RAM memories to the DUT.
Okay, understood.
Okay, clear everyone?
Santi, what is register block? That block.
Register block in the sense it contains registers and the memory maps. Memory map in the sense it contains offset address. In register block we don't have the offset address, but in memory map we have the offset address. In the register block, suppose it's a register block, in register block we have only the register fields. First I have written the register fields, right? We'll have the register fields and we will have the memory blocks. This one is a memory block.
Okay.
This register block will be there in the memory map. This register block, whatever the top fields are there, fields plus this memory one will be there. For this particular registers, there will be a offset address. Suppose here field 1, field 2, register 1, register 2, and it's a memory map 2. So same here field 1, field 2, and the register map 2. For this we have the offset address 0 into 0x 0 0, 0x 04, 0x08, like that. Whatever, if there are 10 number of registers, each register 00, 04, 08, 0c, like that again, 14, 18, 1c, 24, 28, 2c, like that. Every memory mapping, that depends on how much you are incrementing. If you increment +4, or if you are incrementing +1, then 00, 01, 10, 11, like that. Every register it will allocate the memory location. That's what memory map we tell, which contains offset address and register data. Okay, clear?
Yes.
Others, any doubts? Okay, so here I'm telling it as a field. So field 1, field 2. So in each field, suppose it's a register 1 and it's a register 2. Okay, memory 1, memory 2. This register 1 is declared with the 7 down to 0. That means number of fields will be 7 down to 0, and this register is declared with the 3 down to 0. So number of fields will be 3 down to 0 will be there. Okay, so that is what the register size. But here in this register size, how we will declare this register size, we need to understand that thing. Okay, so have you noted everyone these things? Anyway, I will share you the material also, but it takes some time. So register fields, how it will be there. 0, 1, 2, 3, 4, 5, 6, 7. Each register having some different names. Okay, suppose register, whatever the register you have taken, there will be some length of the field, length of the character here, and there will be a busy state for one field. There will be a receiving value. So what is the received data? And also like transmission negative, and there will be some assertion related will be there. So these all fields you need to declare in the register file. Okay, so based on that you will be storing each data. Suppose 1, 0, 1, 0, 1. So in the DUT, you will be having this data in the design. So each one, which field is related to which value. Based on that only, we need to create these values. Okay, I will discuss this thing more clearly in the next session while writing the program. It would be a bit confusion as of now. As of now, we will discuss the theory part overall. Okay. Everyone clear till here? Everyone understood what is mean by memory map? Memory map in the sense this memory model. Okay, in this memory model we'll be having the memory map. Memory map in the sense it have the information of offset of registers, memories, and the register blocks. Okay, it is used to identify which bus agent register basis is executing. Okay, so there will be offset address and also whatever the register name or memory name or block name. So it will be having offset as I told 00. You are incrementing as a 20, 40 or 60 or F0 or else 0, 01, 10, 11 like that. So this particular offset value is for register A and this particular offset is for register B and for register C, and sometimes it represent for memory block and some memory 2 block, and there will be some sub blocks also. So this is what memory map. It will be having the target to DUT handles and also target to sequencer handles. Based on this, we will generate the data in the sequencer. Okay. Clear everyone? See here, register 0, register 1, register n. So in the register, this is what register map, whatever reg 0, reg 1, reg 2. These data is getting from sequence library.
One question.
Yeah, tell.
Let us suppose that the address space is contiguous. So let us say our first register has an offset of 0x0010, just an example, and the next register is just, I mean, is the, I mean, it's just, it's next to R1 or R0, whatever. So is there a way to um, avoid avoid giving those offsets manually and just add the previous register's address plus the offset?
Previous address register plus offset. You are creating new registers here.
No, I'm talking about offset. So
Uh,
let's say if I, yeah, go ahead.
okay. Offset address is totally based on your type of transaction, whether you are taking some wrap type or increment type. If you know AHB protocol, did you know AHB protocol, anyone?
Yes, ma'am.
Suppose if you see here in AHB protocol, how the byte addressing we are considering. Suppose if you see here how the byte addressing or memory addressing we are considering here, we consider in terms of increment or wrap address. Okay, so 0 into 34, 0 into 36, 0 into 38, I mean 34, 36, 38, 3A, 3C, 3E. Incrementing plus 2 plus 2. So in this size, we need to consider total 8 number of transactions. Okay, so within the range memory addressing we are considering same for registers also similar, but here within one transactions we have taken 8 different values, 8 different transactions. So in registers based on this 0 into 34 will be allocated to one memory, 0 into 36, 0 into 38, 0 into 38, 0 into 37, R1, R2, R3, R4, R5. So these are the register offset address only, not data. Okay, same offset address will be there in the DUT addresses also. In DUT also same registers will be there, R1, R2, R3, R4. Same addresses will be there because both at test bench side and DUT side, both addresses must be same. Then only we can send proper data into that particular address, right? In the DUT register R1, R2, R3 also it follows same 0 into 34, 0 into 36, 0 into 38, 3A, 3C like that. Okay. So in the input side, we do the randomization of data. Whatever the data we are generating, that data we will pass to the particular registers to the DUT. In DUT, into that particular register offset value address, it will be storing that particular data.
Okay.
That picture you will get here clarity. See, in the RAL model left side, register files. These are the register files. In register file, there is a register A, register B, register C, and there is the address mapping. Address mapping means what? In this address mapping, you will be having the offset address. So for register A, what address? 0 into 0, 0. For register B, like a 3, 4 or 3A, 3B, 3C. So register C, that particular offset. Whatever the offset values are there here, particular address, same here also for register A, register B, register C will have same offset address. Okay. So here we will do the randomization of data also. That data will be sending to DUT and it will store the data to particular register. Okay.
Okay. Yeah.
Next, any doubts? Others? Have you understood what is meant by register mapping and memory model, register model? Okay. Next, coming to the adapter here. What is meant by adapter? Normally, in a sequencer, how do we generate the any signals like random data? Directly we randomize the binary data through the sequencer we will send to the driver. Okay, so that is what bus transaction where it understand only binary data. Driver will accept only binary data. Okay, driver never accept the register data. Okay, but here whatever we are randomizing, it's a register data, like offset data before I have shown you, right, in the. So 0 into 3, 4, 3, 6, 3, 8, 3A, 3C. This data will not understandable by internal processor or internal system. Simulator doesn't understand this offset address. It understand only binary data. Okay. So to convert that binary data, to convert this offset address to binary data, which is understandable by driver, for that purpose, we use the adapter block here. Okay, this adapter block will exchange the transactions, like it converts the registered transactions to the bus transactions. Whatever the registered data, suppose offset value is 0 into 32. So this 0x32 will be converted to some internal, whatever the binary value is there for that address, that value will be converted. So this binary value will be transmitted to the driver through adapter. Okay, so this register sequence will be converted to the bus transaction that will be sent to the agent. Okay, so this is what the agent. In agent, there will be a sequencer. Sequencer is getting the data from adapter. That sequencer will send the data to the DUT. Everyone understood what is meant by adapter? It converts the register transactions to the bus transactions as well. So after driver need to send same transaction to the DUT here. So DUT will get same data here, register data, and that registered data again sending to the monitor. Monitor also accept a binary data only. Okay, again this monitor will be sent to the adapter, right? Because again we need to store our main actual data into the sequence library. However, we are getting the data to the scoreboard to print the output. At the same time, we will store the data into the sequence library. In register, in a RISC-V processor, we have the stages, right? The pipeline stages like fetch, decode, execute, memory, and write back stage also will be there. Write back stage is just to store the data within the processor itself. Okay, so like that, to store the data, to update the data every time. Suppose here register 0, address is like a 0x00 or 0x3c. This is a updated value. The data will be updated into that particular address. Okay, so that updated data will be giving from the DUT, and it is a sequence library is storing here. Okay, so that's why monitor will pass the data to the sequence library. But how? Monitor will be having this binary data, but sequencer doesn't accept that binary data. So here also adapter will be helpful to convert the binary data to this address data. I mean, register transactions. Okay, so vice versa. Adapter is used to convert address register transaction to bus transaction, as well bus transaction to register transaction. Is it clear, everyone?
So Prasanti, like from monitor to adapter, it is directly connected, or from how like we get the data from monitor, then it gives back to the adapter. So
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 you
is
can
it
see here, here
okay?
the connection. So you will be getting like this: monitor to adapter, again adapter to reg model. So what is mean by predictor? After adapter, here there is a predictor. Predictor is also one of the main block in RAL model. So anyone know what is mean by predictor?
It predicts the value from the registers, and
Okay,
uh,
and what it do? So predictor in the sense, it updates the response from hardware registers to the register model database. What are the hardware registers? The DUT registers. These
DUT.
registers are nothing but hardware registers. So from these hardware registers only we are getting the data to monitor. Okay, so that monitor is sending to the adapter, because adapter will convert these binary sequences to the register sequences. So output of adapter getting the register sequences. That register sequence response will be updating by using the predictor to the database. Again, from the predictor, if you see, the data is getting to the register A, register B, register C. Every time the data will be updated to the registers using predictor. Okay, so we will do the analysis port, TLM analysis port, because monitor to adapter, and also this side monitor to coverage report, we will connect monitor to scoreboard, we can connect monitor to checkers, whatever. So that's why we use the analysis port here. Okay, clear everyone? How the predictor will look like, suppose if I explain more clearly.
Can you repeat the predictor again?
Okay.
I mean, exactly the usage of where?
Predictor is nothing but it converts, it update the value of registered database. Suppose
Okay.
here, whatever the register A, B, C, we are just passing the data to this sequencer, sequencer to driver, driver to DUT. So in DUT, it getting the values and storing the data. Register A, B, C, it is storing some data. Okay, so that data we need to check at the output side. So how we can check at the output side? That data should get at the monitor. So from the monitor, we will directly write into the scoreboard. But whatever we are writing into the scoreboard directly, that is a binary data. because here also it will be binary data, monitor also will be getting binary data. So directly we can't understand the data into the scoreboard here. Okay, so for that purpose we can use one adapter connection to the scoreboard, or else we can connect adapter here. So adapter will be converted this binary data into actual register address, whatever before offset address is there, that offset address it will be getting. So the predictor will update that offset address and register data to this RAL model. It just update the data, update the response from the hardware registers to the register model database. So this is what the database library, we can call it as a library. If you see here, sequence library. So in this everything, the data will be there. So the register model is updated automatically at the end of each backdoor access cycle or front door. Actually, in RAL model, we have two types. One is a backdoor access, one is a front door access. So can you tell me what is the difference between backdoor access and front door access if you have idea? Backdoor access is nothing but this is what backdoor access in the sense directly from register model to DUT we will connect. But front door access means there will be a agent and a DUT. That means directly from adapter to sequencer, sequencer to driver, driver to DUT we will connect. Same whatever we discussed before. But backdoor access means we don't have the agent. We will remove the agent directly from here to here we will connect. We will see how we will connect in a backdoor access. Okay, everyone clear till here?
Hello.
Actually, I have a doubt, ma'am.
Yeah.
Inside our register, we store data, no? So that data is binary, or it is also somehow different.
In DUT we will share the we will store the binary data only to the offset address, because it have the functionality, right? We write the hardware design. According to the design, it will store the data.
So actually, address of a register is offset value, offset address. It is different from binary. And when it comes to DUT, inside our DUT, we have register, and
Same
that
binary
register
data.
contains. Oh, okay, okay.
Yes. Same offset address will be there in the DUT. Whatever the binary, suppose here for 3C, this is the binary value. And here in DUT also there will be a 3C offset address. So this binary value will be matching to 3C. Internally there will be a converters. So through that internally there will be lot of like functionality converters will be there. We are just discussing top level only, right? Internally there will be lots of things, connections.
Okay, okay.
Okay, everyone
Hello.
understood what is, yeah, tell.
Oh, no, no. Actually, in RAL, we can use without driver because register model, we directly use the register values, right? So it can drive the value to the register. So can we use the RAL model without driver?
Yeah, that's what I'm telling here. Backdoor access, we don't use the agent. We remove the agent in backdoor. In front door access, we put the agent. If we put the agent, obviously there will be a driver.
Okay, right.
Okay, so predictor. I think everyone got the clarity about the predictor, right? So whatever the register desired value is there, it will be matched to the mirror value, and it will update the so there will be two different values. This is what actual our register R1 register. So R1 register have some data 0, 1, 0, 1, 0, 0. So it will be having some mirror value. Mirror value means predictor. Through the predictor, we'll be getting some mirror value. Same here. Based on the front door access, it will write and read the data. It will update the value into the register database. Okay. The register model content at the end of the front door access can occur using these. And also there will be three prediction methods. One is a auto prediction, one is a explicit prediction, one is a passive prediction. So what is the difference between auto prediction, explicit prediction, and passive prediction? We will discuss one by one clearly. Okay, I will draw the diagram, predictor diagram here itself. So what will be there in the predictor? There will be a RAL model, same before whatever there. So here register model, or else I will explain here only. So coming to the predictor, here there is a RAL model. To the RAL model, how the sequences are getting. Here register sequence will be getting. Okay, and predictor DUT. So auto prediction in the sense it just update the mirror value. At the end of the front door, I just read the data. If any failure occurs, it gives the failure detection. Okay, so one of the limitation is it fails to observe the bus operation that does not originate from the register. That is only one thing, auto prediction. Automatically it will predict the data. Okay, but explicit prediction in the sense here in automatic prediction we don't use the predictor separately. Automatically whatever the monitor data is there, that will be detected. But it in the register model it doesn't detect the binary data. That's why one of the limitation in auto prediction is it failed to observe the bus operation that does not originate from the register. So auto prediction we mostly doesn't use. Okay, explicit prediction. Explicit prediction in the sense whenever the implicit prediction is turned off, that means automatic prediction is turned off, then we use the explicit prediction. Okay, so the predictor receives the bus operation observed by a connected bus monitor. Here we will connect the bus monitor. So it update the mirror and desired register at the end of the front door access and read with read and write cycles. And it also have the ability to observe the operations from the register sequence. So this method is called explicit prediction method. Okay. And everyone understood till here?
Ma'am, can you
Uh,
explain explicit prediction again?
Explicit prediction is same this model only. We will connect a extra predictor. In a automatic predictors, we doesn't connect any predictor. Internally, the system will predict the data from the monitor, which is a binary data. But binary data will not accepted by the register model, right? That's one. That is the limitation with the automatic predictor. In explicit predictor, we use this predictor externally. In automatic predictor, we don't have this block diagram. In explicit predictor only, we have this diagram. And also we have passive prediction. Passive prediction means passive will integrate only if it is required the register model with the bus monitor, because register model will not integrate with the bus sequencer here. So it cannot be used to write and read the registers and memory to the DUT. So that's why to verify the current value whenever it is required, then only we use the passive prediction. Passive prediction also same, but with this agent we doesn't connect the register sequences, we connect the bus sequences directly. This block diagram we don't have at bus, I mean at agent. Directly we will consider the bus sequences. This is what register model. This register model will be connected to predictor at the output side, and there will be an agent here, agent. And before we have connected this reg model here, right? But we don't have the reg model there. We will send directly bus sequence to the agent here. Okay. So agent to DUT, again DUT to monitor will get the data to predictor. Predictor will store the data to reg model. So how the bus sequences will be converted to the reg sequences? You need to get the answer for that. Understood, everyone? Here actually we will connect the register model to agent before we have connected register model to agent. But here in this case, in passive prediction, we don't connect the register model to agent. If you don't connect the register model to agent, you will be not getting the register sequences here, and the register sequences are not connecting to agent. We are directly connecting the bus sequences to agent. Okay, so how these bus sequences will be converting at the DUT side to registers, and how the register data is getting here, and the predictor will store that reg data, because here we are connecting the monitor will convert the adapter data, adapter will convert a monitor data to reg sequences. That reg sequences, this predictor will be stored to the register file. That's what we call as a passive prediction. Input is a bus sequences, output is a reg sequences. Okay, but my question is how these bus sequences are connecting to the DUT, how bus sequences are directly storing into the DUT. That's what passive sequence. Input is a bus sequence, output is a register sequences.
In between, we may have some adapters to convert our red sequence to binary.
Okay. We don't have any adapters here. So here we are connecting only bus sequences, but is it possible to write and read the register into the memory, or will it only track and verify the value? That is also possible, right? Maybe it won't write the data into the register. It doesn't read or write the data, but it just track the data from DUT to register model. In this case, in passive predictor, just it predict the data from the driver on, data from the DUT only. It doesn't send the register data to the agent. But in explicit predictor, we are passing the reg sequences to agent. So this reg data will be sent to the DUT. From DUT, the reg data will be converted to the reg model by using predictor. But in passive predictor, it just verify the current data only. It doesn't write or read the data into the DUT. Clear, everyone? Go through the recorded session again. Today we have discussed on register model, what is meant by register RAL model, what is the difference between register map, adapter, predictor, okay, how the register sequences are converted to the binary sequences using adapter, and what are the different types of predictors, passive predictor, automatic predictor, and explicit predictor. Okay, so all these concepts, everyone go through the session once again. You can refer some more materials in the internet or wherever, so get the overall clarity. So once you got the clarity, in the next session we will discuss on methods, which methods we use to write and read the data. Mostly in a RAL model, we have the methods like get, put, peek, get, set, peek methods are there. So we will discuss what are these different methods, like in backdoor access, front door access, like a peek, poke methods. So how we can write the data, how we can write some simple programs. We will discuss these things. Okay. Clear everyone till here? Any
Yes,
doubts?
ma'am. Actually, bus sequence means it is binary or it is
Binary,
red sequence. No? Okay.
binary sequence.
So passive predictor is similar to can we relate it to passive agent which will not do anything but just monitors like that?
Yes,
Okay.
yes, it's correct. Passive agent also same. We disable the sequencer and driver, just it monitor the data, it just verify the data. In the same way, to just verify the current values of registers, that means we can get the data from DUT, but to the DUT we cannot send the data. Okay, whenever you just want to verify or just want to check the data, then you can use the passive predictor.
Okay. Okay.
Okay. So yeah, any other doubts? Mostly by end of the program, end of the workshop, I will share you the clear PPT. We are working on the block diagrams, all these block diagrams. Okay, so you will be getting clarity by that time. But meanwhile, you can refer recorded sessions and make a notes. Any other doubts from others? Gurshant, any doubts? Vinita, Vishal, Tamanna.
Not as of now, Prashanti.
Okay. Okay, then we'll see in the next session.
Thank you, ma'am.
Yeah,
Thank
thank you.
you.
By next session, everyone get the clarity. Okay, like how the predictor and adapters are working. So while we are writing the program, you can understand easily. Okay, thank you all.
Thank you.